Okay, let's solve a power series differential equation question. If the series y of x equals this generic power series here is a solution of the differential equation 3y double prime minus 3x squared y prime plus 3y equals 0, then a general solution of the same equation can be written as y equals c0y1 plus c1 y2, where y1 is 1 plus this other power series starting at 2, and y2 equals x plus yet another power series starting at 2. So the goal of the problem is to find the first three terms of both AN and BN. So A2, 3, and 4, B2, 3, and 4. Before we get started, just a couple of things I want to point out. This C0 and this C1 here are not arbitrary C0 and C1. So unlike a lot of differential equation questions, these are not arbitrary constants. They are literally the C0 and C1 that come from this Cn that is given to us. And the second thing I like to point out is this equation, each of the terms on the left have a factor of 3. So to make all the calculations easier, dividing both sides by 3 to start off with is going to be really helpful. So we get y double prime minus x squared y prime plus y equals 0. It's just another way to write this equation more simply. All right, so here's going to be the general strategy. In order to figure out these 6 terms, we're first going to have to figure out AN and BN. To be able to do that, we have to find out y1 and y2. And to do that, we have to find out y, which is going to require finding out some information about Cn. Okay, so focusing just on Cn is going to help us get to these 6 terms for our final answer. And the general strategy to figuring that out is because this is a solution of that, if we plug it into this differential equation, it should be true. And what I mean by plugging it in is we literally write y there, we take its derivative and put it there, we take its second derivative and put it there. So obviously we're going to have to start off by finding the first and second derivative of this function. To find the first derivative, well, if you take the derivative of a power series, is just a bunch of stuff being added together. So with derivatives, you can just do the derivative of each term separately. This is a constant times x to the n, so we're going to use the power rule, bring the n down, and subtract 1. And then we'll do the same thing for y double prime. Here's what we get after all that. So y, I just rewrote y over here. Its derivative, y prime. The n comes to the front and you subtract 1. We get n cn x to the n minus 1. And also something to keep in mind, this like initial value of n here also gets incremented when you take its derivative. This is reflected in the fact that the constant term of this series becomes 0 when you take the derivative. So it drops off a term, and you can verify for yourself if you plug in 0 for n here, you do indeed get 0. And then for y double prime, the derivative of this one, you bring the n minus 1 down to the front and make it an n minus 2. That's exactly what we have over here. And then this also gets incremented. You can verify if you plug in 0 or 1 for n, you'll end up getting a 0. Now I'm just going to replace y double prime, y prime, and y in this equation here, and we'll do a bunch of algebraic simplification to figure out some information about Cn. So this is going to be a whole lot of symbols and letters being pushed around everywhere. I've color-coded the red, green, and blue here, so you can keep everything organized because it's going to take a lot of steps and a lot of symbols being pushed around. So let's do it. So this is what we get when we take this brown equation, replace y double prime with the thing in blue. So it'll be minus x squared, the thing in green, and then plus the thing in red. And the goal at the end of this is to combine these 3 sums into 1. In order to do that, that takes 3 steps. So the first step is to make sure that none of the sums have coefficients in front of them. So by dividing by 3 earlier, we got rid of coefficients in front of the blue and red sums. Now we're just going to take this minus x squared and put it inside of this sum here. So we're going to turn it into a plus. We're going to put a minus here, and then the x squared times x to the n minus 1 That's just adding 2 x's to it, so it'll become x to the n plus 1. Okay, so that's what happened here. The blue and red terms stay the same. The green term became a plus, the minus 1 inside, and the x to the n minus 1 became x to the n plus 1. So that's the end of step 1. They have no coefficients in front of them. Step 2 is going to make it so that these 3 exponents of x are the same. And to do that, we have to do what is known as an index shift. This is arguably the hardest part of the problem. I find that a lot of students struggle with index shifts because they can be kind of confusing. I think they're very analogous to U substitutions with integrals. This is kind of like the discrete summation version of that. Basically, we're going to introduce a new n. Let's focus on this blue term here. And that new n, I'll just call it capital N for now. We want to set it equal to that exponent lowercase n minus 2, and that will make this exponent a capital N. And obviously, we're going to have to substitute in for these other lowercase n's as well, but we're going to do a similar thing to make sure that each of these exponents become capital N as well. Starting with blue, the index shift we are going to do is we're going to take capital N, so for the y prime term and the y double prime term in blue, capital N, we're going to set it equal to this exponent, lowercase n minus 2. And therefore, lowercase n will equal capital N plus 2. So that's what that index shift would look like. This blue term right here, the n minus 2 gets replaced with capital N. Each of these n's here get replaced with capital N plus 2. So we get n plus 2, n plus 1 over here, and c capital N plus 2 here. As for the bounds, well, when lowercase n is 2, capital N will be 2 minus 2, which is 0. When lowercase n is infinity, capital N will also be infinity. And then we're going to do a similar thing for the other two sums. So for the green sum, we'll let a substitution. So we're substituting this lowercase n plus 1 in for capital N. And therefore, lowercase n will equal capital N minus 1. So that index shift looks like this. So the green term here, and then the negative lowercase n becomes n minus 1, Cn, capital N minus 1, and this exponent just becomes capital N. When lowercase n is 1, capital N will be 2. And when lowercase n is infinity, capital N will also be infinity. And then finally on the last term, this is already n, so no need to do any like shifting here. I'm just going to replace the lowercase n with a capital N for consistency. Okay, so this next step right here, applying those index shifts, will change this blue, green, and red sums into their shifted versions. So the blue becomes that, the green becomes that, and the red becomes that. So that's the end of step 2 for combining the sums. The final step is to make it so that these 3 numbers here are all the same. And you notice the index shift also kind of messed with those numbers. That's why we did the index shift first. Now, in order to make it so that these 3 numbers align without messing up these exponents, we're going to make it so that they're all equal to the biggest one of the 3. So the biggest of 0, 2, and 0 is 2, which means we need to pull out the n equals 0 and n equals 1 term from both the blue and the red sums. Remember, this is basically just like plugging in n equals 0, 1 all the way up to infinity. So if we plug in 0 and 1 and bring them out, we can change this 0 to a 2. And then same thing over here. Let's actually calculate what we get when we plug in 0 and 1 for n. In the blue sum, if we plug in 0 for n, we get 2 times 1 c2 x to the 0. And if we plug in 1 for n, we get 3 times 2 c3 x to the 1. Okay, so plug in 0, 2, 1, c2 x to the 0, plug in 1, 3, 2, c3 x to the 1. And then 2 times 1 is 2, x to the 0 is just 1, and this becomes 2c2. 3 times 2 is 6, x to the 1 is just x. So we get 2c2 and 6c3x. And then for the red, we Plug in n equals 0 and n equals 1 to this one as well. So we're just going to get c0x to the 0 and c1x, which is just c0 and c1x. So in doing so, these indices now become 2 as long as we add in these extra 4 terms here. Now, in one step, I'm going to write all 4 of these terms on the outside and combine the blue, green, and red sums finally into one big sum. Now, the sum will still be from 2 to infinity, but they each have an x to the capital N in them, which I'll factor out. And inside, we will just get this plus this plus this. So let me write out the capital sum first. It'll look like this. 2 to infinity, take this, and that's all times x to the n. And on the outside, we add these 4 terms together. So I'm going to group them up. We'll do the c0 plus 2c2 first, because those are just constants. And then I'll factor the x out of these two. So we'll just get c1 plus 6c3. And that's the end of the third step. Now we've combined these sums into one with a couple of extra terms on the outside. If you'll notice, this term is the constant term. This is the x to the first power term. And since this is n equals 2, this is x squared, x cubed, and everything past that. Point of doing all this is because since this is equal to 0, it means it's equal to 0 for all values of x. Or in other words, all the coefficients, the constant term of x squared, of x cubed, those should all be equal to 0. It's like equal to the 0 function in that way. So we can conclude that the orange here, c0 plus 2c2 should equal 0. The green, c1 plus 6c3 should also equal 0. And in blue, this is actually an infinite amount of coefficients. Each of these will equal 0 for any value of n that's 2 or greater. So n plus 2 times n plus 1, cn plus 2, minus n minus 1, cn minus 1 plus cn, and that's all equal to 0 as long as capital N is greater than or equal to 2. Okay, let's take a break and collect what we found. We have these 3 equations with a bunch of c's in them. I mentioned that that gives us some information about cn. Back over here, the y of x we were looking at only had c0 and c1 in them. So therefore, I'm going to try to make it so that all of the cn's are in terms of just c0 and c1. Okay, so that's my logic. In the orange box here, I'm going to solve for c2. So c2 will be equal to negative 1/2 c0. c3, I'll solve for c3 here. I'll get c3 equals negative 1/6 c1. Okay, so I'm getting all of the cn's in terms of just c0 and c1. And in this blue equation here, it's generally a good idea to solve for the c with the largest index. So of n minus 1, n, and n plus 2 is the biggest one. I'm going to add this over, subtract this over, and divide by n plus 2 times n plus 1. I'll do that all in one step. So cn plus 2 is this minus this divided by this. That's true for all values of n that are greater than or equal to 2. Let's take another pause here and go back to what the problem was actually asking for. A2, A3, A4, B2, B3, B4. So if I go ahead and take out this yellow part over here, so off to the side, that's the yellow part, C0, Y1 plus C1, Y2. And I just replace Y1 and Y2 with what we were told they were equal to. You'll notice that since these only start from n equals 2 onwards, finding A2, 3, and 4 and B2, 3, and 4 only requires us to look at the coefficients of x up to x to the 4th. Anything bigger than that, and we'd be looking at A5s, B5s, and so forth. So I'm only going to worry about C0 all the way up to C4, because anything bigger than that isn't really helpful for what the problem's asking for. Currently, I know just C0 is C0, C1 is C1, and I already have C2 and C3. So the only thing I'm going to use this really complicated looking equation for is to find out what C4 is equal to. Now, in most differential equation power series problems, you'd use this equation, which is known as a recurrence relation, to try to find like a general form for Cn, but it's a bit too difficult here, and that's why the problem's not actually asking us to find a general like way to write out Cn. It's just asking us for some particular terms of A and B, which depend on C here. All right, so since the left-hand side is n plus 2, I'm just going to plug in that first value of n, which is 2, and that'll turn this left side into C4. So if we plug in capital N equals 2 into the blue, we'll get C4 on the left side, and on the right, we'll get 2 minus 1, C1 minus C2 over 2 plus 2 times 2 plus 1. So the 2 minus 1, that's just 1. I wanted everything in terms of C0 and C1, so I'm going to plug that C2 in here. So I'll get C1, instead of minus C2, it'll be plus 1/2 C0. And on the bottom, 4 times 3 is 12. And finally, just to like write that out as two separate things, 1/2 C0 divided by 12, that's going to be 1 over 24 C0. C1 over 12, that's going to be plus 1/12 C1. So I now have C2, C3, and C4 all in terms of just C0 and C1. To collect that information, which I'll do down here, we have found y of x, which by definition is this sum here, which we can write out like this. C0 plus C1x, dot, 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 all the way up to C4x to the fourth, and then plus a bunch of miscellaneous terms that are not going to be important for this problem. And I'm going to leave C0 and C1x as is. And now I can replace C2 with minus 1/2 C0 x squared, so C3x cubed will get minus 1/6 C1x cubed, and C4 is 1 over 24 C0 plus 1 over 12 C1 x to the fourth, plus some other miscellaneous terms. We are very close to matching up this way of writing out y of x with this way of writing out y of x. We have a bunch of C0s and C1s here, but in this version, the C0s and C1s are factored out. So let's go ahead and do that. I'm going to factor out all the terms that have C0 in them over here. If I do that, I have a C0. I factor that out of C0. I'm left with 1. This one doesn't have a C0 in it. Minus 1/2 C0 x squared, that's going to become minus 1/2 x squared once we factor the C0 out. And over here, I'm just going to factor out this part of the x to the fourth. So we're going to get a 1 over 24 x to the fourth within this C0 parentheses here. And then plus a bunch of other higher powered terms for x. And we'll do the same thing for C1. We have a C1x, so we'll get C1x and then minus 1 over 6 x cubed with a C1 attached to it, and then a plus 1 over 12 x to the fourth. Now you notice I'm leaving some white boxes here. That's because really what we have is a sum inside here where the x term just has a coefficient of 0. So I'll just replace the gaps 0x. There's a 0x cubed here. There's a 0 here, and there's a 0x squared here. These two versions of y of x now line up. We have C0 times 1 plus a term with 0 plus a bunch of stuff starting with x squared. And then for C1, we have x plus a bunch of stuff starting with x squared. So really what we found is that this sum here, starting with x squared, that is just the AN sum right there. And this sum here, starting with 0x squared, is the BN sum. Therefore, finally, we can write out A2, A3, and A4. So A2 will be -1/2. A3 will be 0. And A4 will be +1/24. And for B, we will get B2 is 0, B3 is -1/6, and B4 is +1/12. And that's it.